Good day, everyone. My name is C. Capadiso, and together with CHELE02, we will be discussing our topic about ceramics, entitled Ceramics, Boon or Bane. And in this presentation, we will explore the different areas concerning the ceramic industry, as well as their impacts socially, technologically, and environmentally. We will also discuss how sustainable ceramics really are. And in this presentation, we hope that you will learn more about ceramics, as well as how it can positively and negatively impact us and the world around us. Let us kick off the presentation with the introduction. So, what are ceramics? Let us start with its definition. Ceramics are by definition natural or synthetic organic, non-metallic polycrystalline materials. This category of materials includes things like tile, bricks, plates, glass, and toilets. Ceramics can be found in products like watches such as quartz tuning forks, automobiles such as spark plugs, and ceramic engine parts found in race cars, and phone lines. They can also be found on space shuttles, appliances, and airplanes. Depending on their method of formation, ceramics can be dense or lightweight. They are shaped, used into desired forms by generally taking mixtures of clay, earthen elements, powders, and waters. Once the ceramic has been shaped, it is fired in a high temperature oven known as kiln. Often, ceramics are covered in decorative, waterproof, paint-like substances known as glazes. And ceramics are considered as one of the greatest and earliest, most useful successes of humankind, in part because they represent how humans learned to control fire and manipulate clay. Ceramics were among the first objects to be manufactured, and owing to their various applications, their importance in material culture has remained over millennia and still persists today. Moving on, let us discuss the physical and chemical properties of ceramic materials. Ceramics possess unique properties due to their ionic and covalent bonds. These properties include high hardness, high resistance to corrosion and chemical attack, high weather resistance, high melting point, high working temperature, high elastic modulus, high dimensional stability, good wear resistance, good electrical insulation, as well as high compressive strength. However, ceramics also have weaknesses, which includes low ductility, low thermal expansion, and medium to low tensile strength, as well as poor impact strength, low thermal shock resistance, and we have brittleness. These characteristics make ceramics suitable for various applications, but also present challenges and certain issues. Ceramics are also used in different ways, and here I will discuss some of the industries that use ceramics and apply them in their respective fields. First, we have the construction industry. Used in structural elements, ceramics are employed in both shallow foundations and building superstructure in medium-sized and ground floor buildings. They are also used as ceiling and subdivision elements. Some examples of this include bricks, hollow elements, and tiles. It is also used for cladding, which is one of the most common use of ceramic materials in buildings. Cladding is the application of one material over another to provide a skin layer. Cladding allows ceramics to be used in a variety of technical and decorative functions. Terracotta and fire clay are the common types of ceramics that are used in construction. Moving on, let us discuss and tackle the applications of the ceramics in electronics. Now we have the ceramics, which is found in semiconductors, insulators, and piezoelectric devices for electrical and electronic components. Ferroelectrics are used to create high dielectric capacitors and non-volatile memory devices. Ferrites play a crucial role in storing data and information. Solid electrolytes are used, which is instrumental in the storage and conversion of energy. Piezoelectrics, on the other hand, are essential for sonar technology, while semiconducting oxides have been pivotal in monitoring environmental conditions. And all of the things I mentioned possess ceramics in their functions. Ceramics are also used in PCBs, display panels, and magnets for data storage and electrical installations. The other applications of ceramics can also be found on the table that is presented on the screen. Let us move on to the applications of ceramics in renewable energy. First, we have the solar panels and photovoltaics. Ceramics play a vital role in solar energy, particularly in the production of solar panels and photovoltaic cells. Ceramic materials are used in solar cells to enhance efficiency and longevity. Advances in ceramic coating have further improved the performance of solar panels by increasing their ability to absorb sunlight and convert it into electricity more efficiently. We also have thermal energy storage, and in concentrated solar power or CSP systems, ceramics are used for thermal energy storage. These systems rely on ceramic materials to store heat generated from sunlight, which can be converted into electricity when needed. The innovations in ceramic materials for thermal energy storage have also significantly improved the efficiency and reliability of the CSP systems, making them more viable for large scale energy production. Lastly, we have the use of ceramics as in the electronics as turbine efficiency for turbine efficiency. In hydroelectric power generation, ceramics are used to improve turbine efficiency. Ceramic coatings reduce friction between moving parts, and because of this, it enhances the overall efficiency of turbines, which leads to increased energy output and reduced operational costs.
Now that we know what they are for, let's now move on to how they were formed. So, traditional ceramics starts by crushing. So, it is actually important to consider how you would uh, treat your raw materials or your ore because it affects uh, the processing or the sintering of your material. So, if the output of the crushing is coarse, you would have a poor forming and sintering process. On the other hand, if the particles were fine, it would be a good way to process your material to ceramics. So after that, the crushed materials are um, conveyed to the blending. So blending is the one responsible for the yield, the quality, and the workability of the product. So sometimes you can add other materials other than clay particles that would help in the properties that you would like to achieve when producing ceramics. Now, the third step to the production is kneading. So this one is mixing with water to form modern feed. So it is comparable to when you're making a slime or you're making a dough. You can actually knead it so that it would be easier to to form, which leads us to the fourth step of the production, which is forming. So forming is using metal molds and plaster molds or patterns so that you can create the form of ceramic or the final products that you want. So there are actually various forms of ceramics, which also depends on your application. With that, let's move on to drying. So, drying is the process of removing water from the materials. So, for the last part, we need to do firing. So, firing is also referred to as the sintering process, which for the kiln, you don't actually mold the material, you just heat it to a certain temperature so that it becomes hard. But for glass production, um, it's actually molten before it's formed into glass. So the three main raw material for porous ceramics are clay, kaolinite, and bentonite. So clay is actually the traditional raw material used for porous ceramics. However, since it can cause erosion and also other environmental issues, you can also use kaolinite and bentonite as alternatives. And if you have it available or if it does not yield to the certain amount of raw material that you want, you can actually mix them up. So, as I've mentioned in the production process, we also have the blending. So, blending is actually adding these materials. So, there are other raw materials you can add. So, for example, we have here feldspar. So, it is used to have a glassy texture or a glassy finish to your ceramic so that you can have a hard and water repellent finish to your product. Flint is also a raw material that you can use, so it is non-clay and it prevents the material from breaking easily. So that's one of the disadvantages of ceramics made out of clay. So quartz is actually a non-clay material as well, and it also prevents the material or the ceramic from breaking easily. They are also a form of silica that allows the ceramic to not absorb water, and also it would not shrink or it would be hard enough to not be broken easily. With that, let's discuss the main agenda of this presentation. So, is ceramic a boon or a bane? So, basically, boon means it's beneficial to us, and also it is practical to apply in our industries. On the other hand, we have here pain. So, pain is gauging how it is detrimental or how it can afflict the environment. So let's start with sustainability. So ceramics can be sustainable in a way of considering the raw materials as renewable. So if you compare it to other materials, it's already in an advantageous place because it is inherently sustainable, as clay is readily available and also easily renewable. On the other hand, have here the comparison of other materials. So we have metal, polymer, and refractory. So as you can see, there are both advantages and disadvantages on the properties of the materials. So I think what's important here is to focus on the performance of the material in a specific application. So ceramics as a sustainable material or a boon when it is recyclable and also easy to clean. So it is easy to clean because again, as we mentioned before, it can have a glassy finish. It is hard, and also it is um, wear resistance. So it has the highest wear resistance as compared to the other materials in the table. So we also have here the efficient production and also thermal insulation. So ceramics are actually known for being able to withstand high temperatures, and also its hardness and chemical non-reactivity allows the material to be formed and densified with heat efficiently. So it operates at high temperature because it involves grinding, kneading, and also the molding. It can be extrusion or injection, and it requires a lot of energy. That's why it can also be unsustainable, which will be discussed later on. Before that, I'd like to highlight how ceramics can be integrated to the circular economy. So, there are actually a lot of studies that um, supports how ceramic waste can be reused and recycled. So here is the summarized version of the use of ceramic waste according to EU 2021. So it was stated that 35% of the ceramics are dissolved in use, so it cannot be recycled anymore. But it is a good thing that there is 20% of the ceramic waste that can be recycled for refractory. So, uh, we mentioned before that one of the advantages of ceramics is being uh, able to withstand high temperatures. So, it's actually applicable for refractory. So, refractory is using the material to resist heat and mechanical stress or chemicals in the industry. So, there are a lot of applications for this, and it's um, it's an evidence of how ceramics can easily be integrated in the circular economy. And then aside from that, we also have the reusability. So reusability constitutes about 27% of the total ceramic waste. So this is applied for non-refractory applications. So it can be reused for another manufacturing of ceramic products or other materials like the cement. So it can be used to blend with cement to reduce the use of raw materials in that industry. And then lastly, we have 18% of unusable waste, which is not as much. It's actually a little chunk of the whole pie chart. So with that, here are the specific applications of ceramic waste. So it can be white or red base, and then it can be processed in a way that it's fired once or twice so that you can yield different types of materials. So this denotes how it can be reused for non-refractory applications. And one of the most notable application is the cement blending. And since it possesses hardness, durability, and high resistance to physical compounds and organic biological dilapidation, it's actually beneficial to mix your materials with ceramic waste. And to be specific, concrete uses such waste to enhance its durability and energy efficiency and construction and insulation. So, since it is resistant to heat, it can be used to insulate your bricks or your concrete. And then there is also a novel application of ceramic waste, which is the catalyze or the catalyst synthesis, and it is a cost-effective way to produce biodiesel. So it actually allows the transferification of soybean oil in one of the studies in 2018, and it was stated that if you add the catalyst, it actually yields to a 99.3% conversion. But of course, ceramics is also a double-edged sword, so it can also be unsustainable in a way that it requires high energy consumption. So I have mentioned before that it's used for grinding, kneading, and molding, which all require high energy consumption, and it is also typically produced using fossil fuels, which is we all know is detrimental to the environment through emissions and also energy use, and then um, or energy demand rather. And then we also have here the non-recyclable waste. So even though there is a possibility to recycle the ceramic waste, it's irresponsibly discarded or not properly allocated for recycling and reusing. We also have lastly the extracted irresponsibly. So in any production, everything should come in moderation. So if you extract clay, even though they are renewable, they can still be potentially hazardous to the environment because uh, if you over extract clay, it can cause landslides, erosions, and also deforestation, habitat disruptions, and the like.
Let us discuss about the socio-political impacts of ceramics to further understand its contributions and the challenges it presents to our society and to the humankind. Starting with its social impacts, we have community displacement. Because of the raw material extraction, land conflicts and displacement can arise given that the raw materials needed to make ceramic products need quarrying. We also have poor labor conditions, and because of some ceramic industries reporting exploitative working conditions as well as child labor. This is morally concerning because the ceramic industry is a big industry and many companies profit from it. Next one, we have health issues because the workers may suffer from respiratory problems when working in the ceramic industry due to the fine dust exposure when doing quarrying and heat related illnesses due to the high temperature nature of the production process. Lastly, we have economic inequality, and this is because of the large corporations dominating the market, which exploits cheap labor while generating high profits, widening the gap between the workers and the industry owners. Now, let us discuss the policies, incentives, and standards that affect the ceramics adoption as well as managing the supply risk. First, we have the Department of Trade and Industry Bureau of the Philippine Standards or DTI-BPS. The DTI-BPS is responsible for developing, implementing, and promoting standardization activities in the country. It has established multiple technical committees comprising experts from various sectors to formulate Philippine national standards, also known as PNS, and adopt international standards, including those from the International Organization for Standardization, or ISO, and the International Electrochemical Commission, or IEC. Next, we have in terms of incentives, the Philippine government allows and offers various benefits to encourage investment in the manufacturing sector, which includes ceramics. The Omnibus Investments Code of 1987, as amended, provides fiscal and non-fiscal incentives to enterprises engaging activities listed in the Investment Priorities Plan or IPP. These investments may include income tax, holidays, additional deductions, and duty exemptions on imported capital equipment. And to qualify, enterprises must register with the Board of Investments or BOI and engage in preferred areas of investments identified in the IPP. Now, we also have the Republic Act 7942, also known as the Philippine Mining Act of 1995, established with to with a framework of exploration, development, and utilization of mineral resources. It includes provisions for quarry permits, which are required for the extraction of raw materials needed for ceramic products such as clay, And these permits are issued by the provincial or city mining regulatory board and are subjected to specific terms and conditions to ensure sustainable resource management. Now that we know the environmental and sociopolitical challenges tied to ceramics and the ceramic industry, what are the opportunities for innovation and improvement? First, let us have cleaner energy use. Transitioning to electric kilns powered by renewable energy can significantly cut the carbon emissions. This is because traditional kilns rely on fossil fuels such as natural gas and coal, which contributes to greenhouse gas emissions, as we all know. And by shifting to electrical kilns, using solar, wind, or hydroelectric power, manufacturers can reduce their carbon footprint and promote cleaner production methods. For the second one, we have sustainable raw materials. And recycling ceramic waste into new products supports a circular economy. And instead of discarding defective or broken ceramics, the manufacturers can repurpose them into new materials, which reduces reliance on virgin raw materials. This process minimizes environmental degradation associated with mining and quarrying and conserves resources, which in turn lowers overall production costs. Next, we have efficient manufacturing. Microwave assisted drying and firing reduce energy consumption by up to 99%. This advanced technique improves heat transfer efficiency, allowing ceramics to dry and fired more quickly and evenly. As a result, manufacturers will experience lower energy costs and shorter production times, as well as reduced emissions compared to traditional kiln firing. For the last ones, we have stronger environmental policies, which is tied to fair labor practices. The implementation of stricter environmental policies and financial incentives can encourage manufacturers to adopt sustainable methods. And the governments can enforce regulations that limit emissions, mandate recycling programs, and provide tax incentives for sustainable practices. Additionally, fair labor laws can be strengthened to ensure safe working conditions, prevent exploitation, promote ethical employment practices within the ceramic industry.
Knowing all this, there's still a question if there's a future for ceramics. And since we mentioned before that one of the key unsustainable features of ceramics is the energy efficiency or the energy consumption, we identify the barriers on energy efficiency. So, as you can see on the right, there is a spider graph provided by Manrique et al. In 2018, which tells us the values of the barriers on energy efficiency in the production of ceramics, particularly. So, first, we have here cost. It's actually specific to hidden costs. So, hidden costs, by definition, are those costs that are not incorporated in the initial investment valuation, and usually it results into impediment on the application or the implementation of new technologies that are more energy efficient, because it is actually important for the companies that produce ceramics to know the operational details, the adaptations, and also the supplies that are required if they are to implement new technologies. So here, net shape manufacturing, which is actually important because energy consumption can be reduced when you have an efficient production process. So if the initial step already has your final shape intact, it can allow you to reduce your energy consumption in terms of molding, kneading, and also um, the molding of your material in with heat. And then we also have the barrier on corporate values. So there is noticeable lax regulation on the implementation of efficient energy systems because aside from ignorance, there is also um, limited behavioral efforts in the corporate level directions. So, lastly, we have here the risks. So, it's also a huge indicator of impediments in energy efficiency because it the risk of applying or integrating energy efficient technologies in a certain plant or manufacturing facility is the market fluctuation. So, decision makers are usually hesitant to upgrade their technologies as they consider the profitability profitability of the production. So to address these concerns, there are actually a lot of studies already on the green chemistry or green engineering involving ceramics. So since ceramics are hard and they are easily contaminated by the material used to grind them. So let's say the equipment, if you're going to be grinding in a ball mill, one of the key problems in this process is the contamination of ceramic raw materials. And aside from this, it also cause damage to the equipment itself. So, since ceramics are hard, they often grind the metal surface of the mill almost as fast as how the mill crush the ceramics. So, the salt-gel process aims to address this problem and also to maintain an environmentally friendly standpoint. So, the salt-gel process involves the hydrolysis reaction to form a cloudy aqueous dispersion called a sol, and the sol contains particle of the metal uh, or semi-metal hydroxide. So as the reaction proceeds, molecules of water are eliminated between the hydroxide units in a condensation reaction. So in equation 12.1.3, we have here the condensation reaction, and it involves the particles fusing together to produce oxide bridges. So uh, the particles become linked in a three-dimensional network that causes the solution to form a gel. So imagine this chemistry starts with a highly pure silica chloride, and it proceeds by the reactions shown on the screen. So once we get the sol gel, it can be identified as a ceramic coating to address the issues I mentioned previously. So we also have green engineering applications or efforts. So first we have here the firing technologies. So there are a lot of new technologies that allows us to be more energy efficient and also a near net shape technology. So these are some of the possible technologies that can address that. So first we have here the roller tunnel kiln. As you can see in the image, there are it is conveyed through rollers, and the chamber has one or two planes of rolls of refractory material on which the pieces circulate from one end to the other. So um, it is important that we maximize um, the processing as much as possible. That's why it's subjected to the process from one end to the other so that you can maximize your processing and reduce the energy consumption in the firing process. So it both of these are important to having a low specific consumption and to have shorter processing time. So imagine if you put your products a little with a little space in between, it will cost a longer time to be processed in the roller tunnel tin compared to when it is stick together and allowed to be heated continuously rather. And then it also allows the incorporation of heat recovery technologies, which enables us to be more energy efficient. And then like the roller tunnel kiln, we also have the tunnel kilns with wagons. So the load moves with the firing zone being fixed. So since the firing zone is fixed, wagons are used to move the ceramic products so that it can also run through the firing zone from one end to another. So the wagons are almost completely filling the interior of the kiln. So aside from being processed from one end to the other, it's also maximizing the space inside the tunnel so that you reduce your energy consumption in the firing process. And aside from firing technologies, we also have other emerging technologies. So, starting off with gasification of biomass and coal, it converts the solid biomass or coal into syngas so that um, it is composed of mainly carbon monoxide and hydrogen. So, it is done in a oxygen poor environment, and the energy efficiency of 70 to 80%. So, aside from that, we also have heat pumps. So, heat pumps are used to transfer energy from low temperature to higher temperature. So it utilizes the low temperature waste so that you can actually use your waste energy into your higher temperature processes that requires a lot of energy. So with that, we also have heat pipes. So heat pipes are sealed devices. So it's important to be sealed, and it is containing a working fluid that transitions between liquid and vapor to transfer heat efficiently. So aside from heat pumps, we also have pipes to transfer your heat in recovering the energy that you used previously. And then we also have other novel technologies like the advanced oxycombustion. So this one is a technique that allows the combustion of energy to be less to have less emissions and also be more efficient. And then it can be construed as a flameless combustion, which obviously will create less emissions. And then finally, we have the organic Rankine cycle. So this is also important to generate electricity from residual heat in flue gases. So with that, we can conclude that ceramics is more of a boon than a bane. It is actually beneficial that it has various applications as a ceramic on its own and also as a ceramic waste. We discuss how it can be integrated to circular economy, green chemistry and engineering, and even um, energy efficient technology. So, with that, what do you think? Is ceramics a boon or a bane? Thank you and have a great day.